Hello and welcome to the Exoplanet Research. In this tutorial, I'm going to be walking you through several steps. I'm going to be giving you the general knowledge about exoplanet and how to register at the AASVO platform in order to obtain an observation code. I'm also going to be demonstrating on how to perform photometry on the images, and then I'm going to be walking you through on how to acquire your own data either from your own telescope or downloading data from the NASA archives. So generally, this is how exoplanets are formed. This is a molecular cloud, okay, and you can see a star is forming at the center, okay. So when the star has formed, let me play it. When the star has formed, what is left over is trapped, is under the influence of that star's gravity, and so they kind of, clump together to form planets, exoplanets, and debris disks such as the exoasteroids, exocomets, and the exo-Earth clouds. So this is not just peculiar to our sun, okay, because our sun is a star, but it's also very common with other stars in the night sky. In theory, most of these stars that we see in our night skies have some form of exoplanets orbiting around them. So, and that is exactly how they form. So, meaning of exoplanets. Exoplanets are planets which exist outside our solar system orbiting stars other than the sun. These planets are also known as extrasolar planets because they are located beyond our solar system in the vast expanse of the Milky Way galaxy and beyond. So the current focus of this exoplanet search are on the stars in our Milky Way galaxy. So this is very important because we're not focusing on stars in other galaxies for now because we don't have the technology to zoom in so deep to be able to investigate them. So the research is restricted with stars in our Milky Way galaxy. So the history of exoplanet started from Italian philosopher Bruno in the 16th century. He speculated that, having understood the way the planets in our solar system formed, the same principle can be adopted to the stars in deep in the universe or in our Milky Way galaxy. So he speculated it, but you know the technology of those days are not enough to prove that. But in 1995, Michael Mayer, this is Michael Mayer and Didier, his student, they embarked on this research and were able to detect the first exoplanet. That exoplanet is named 51 Pegasi b, and up to today, about 5,500 exoplanets have been discovered. By the way, these two are from the University of Switzerland, university in Switzerland, I think. So, all right, there are 5 methods of exoplanet research. Number one of them is the Doppler technique or the radial velocity method. This method was used in 1995 to detect the first exoplanet 51 Pegasi b by Michael Mayer and Didier. So about 1,065 exoplanets have been detected with this technique till today. So what is this method all about? Let's play this video. So if you observe, this is your line of sight, okay? we assume that we are in the line of sight of the two systems. Now, this is the exoplanet and this is the host star. Because of their masses, they are orbiting about a common center of mass, okay? And we shouldn't discuss that now, but they are orbiting about a common center of mass. Now, when this host star is coming towards us, it is blue shifted, and when it is moving away from us, it is red shifted. That is the idea of Doppler effect in physics. So this is one of the methods of detecting exoplanets around the host stars. Then the second method is the astrometry method. About 2 exoplanets have been discovered through this method. What is the astrometry method? In astronomy, astrometry simply means the study of the position and movement of celestial objects. In this case, we are talking about stars. Okay. Now let's play this video, this animation. Now imagine that this is happening. We discussed that this is the Doppler method. Now imagine that you are observing this star from the night sky and you are comparing it with other stars. These other stars are stable, but something seems to be happening with this star. It is some kind of moving, like a kind of a motion. So it's one of the ways you can say that, oh, maybe this star has some exoplanet around it. So 2 exoplanets have been detected using this method. Then the third method is direct imaging, just as the name implies. Direct imaging. This method works well when the planet is farther away from its host stars. About 69 exoplanets have been detected through this method. So in order to use this method, that exoplanet has to be very far away from the host star. And why is this necessary? Imagine, let's take for instance doing solar eclipse in the daytime, doing solar eclipse. If you compare the size of the sun and the size of our moon, it is not even comparable, because of the faraway distance of the moon from the sun and with respect to Earth, they appear to be the same size. So when the host star is far away from when the exoplanet is far away from the host star, they are comparable in sizes, so this direct imaging will work. So it's going to block the sun entirely. Then a lot of us this is a significant number, 69 exoplanets. Then we have the fourth method. So we have the A method. We also have the B method. Okay, let's go to the A method. So this is called transit or light curve method. This method is the most useful of all the techniques. Okay, about 4,122 exoplanets have been detected using this method. So let's play the animation. So you can imagine that you have a host star with exoplanets. So as the exoplanet is transiting in front of the host star, it is going to diminish the light, the total brightness emanating from that host star. It's going to bring it down. It's going to bring it down. It's going to diminish it. Although you may not be able to notice this with your naked eye, but if you use some special tools, you'll be able to know that, oh, the brightness of that star has gone down by some amount. So let me play the video again. And if you also observe that by the way, this is called the baseline. Observe that the depth of the light curve between these two are not the same. And also observe that the sizes are not the same. This one is less deeper, and while this one is very, very deep. So to tell you that it can also be used to detect, to measure the sizes of these exoplanets. So if an exoplanet is very big, you should be able to know. If it is very small, you should be able to know from the light curve. In fact, this light curve provides a lot of information about the star and the exoplanets. So the B part is for multiple transiting exoplanets. So imagine that um, you have multiple exoplanets orbiting uh, a star. So this one here create this light curve. Let us see how this one is going to be. And it was still about to finish, and this one other one just came, and this other one happened. So it created these multiple uh, variations in the light curve. So it is used for multiple systems. So it is almost the same thing with the A part, just that the A part is just for a single exoplanet, while this is for multiple transiting exoplanet system. Then the final one is the gravitational microlensing. It works with the principle of gravitational lensing. Okay, in physics or in astrophysics, galaxies or even some stars that are very massive are able to bend the light coming behind them. Okay, it bends the path. It bends the path like a lens. So about 204 exoplanets have been detected using this method. So let's play the video. So you can imagine a huge star that is radiating light. Okay, I want to pause this. I want to pause this and give you an illustration. This is a massive star emanating light, and this is an observer. So we are the observer. So this is us. Okay, then as this star is coming towards us where we are, okay, we are beginning to see the light curve. Look at the light curve. That kind of light curve it is creating. This is called micro lensing. Micro lensing. So it is bending the light. It is giving it an effect of a lens. Okay, when you pass light through a lens without conversion or diversion, it is going to diverge it or converge it. So it is behaving like that here. So let me play it again. So once this comes to the observer, I want to pause this here. Let me pause it. Let me go past it a little bit. Great. So you see that? Now, if you observe this light curve, you would see that it's a little blip here, a little extra curve on top of that bigger curve. This is caused by the orbiting system around that star, which is an exoplanet. Okay, so this is one of the methods that we use in detecting this. About 204 exoplanets have been detected using this method. It's called gravitational microlensing. All right, then how many exoplanets have been discovered so far? The best place to see the update is at the NASA Exoplanet Archive. So if you type in your Google NASA Exoplanet Archive, it's going to bring you this. Okay, so you would see 5,523. Some people are curious about that. So, and more and more are added on some periods. Okay, like as of the time I checked it, I was preparing this slide. It was on 2nd of October. So if you check now, it might have, more have been maybe have added to it. So naming exoplanets. How do we name exoplanets? I expect that for you to get into this exoplanet, you must be part of our community, and we are very active in the asteroid search. And if you are very active in the asteroid search, you must have noticed how asteroids are named. Asteroids are named in this convention. You see something like 2022, SA192, 2021, this, that. Okay, that is how asteroids are named. Okay, that is for the provisional numbering of asteroids. And after undergoing several studies, they can be given a name of a person, maybe a Nobel Prize, or someone has contributed to the society, or to the scientific community. Okay, that is the convention for asteroid. But for exoplanets or for stars in general, they don't have any proper names. Okay, they have these names that goes by TRES 3, WASP 10, and this and that. And their host stars are given some letters, like in TRES 3, the host star is given uh, TRES 3. The host exoplanet is given the TRES 3b, and this one for the star, the exoplanet associated with this star is given this 10b, WASP 10b. So that is the convention, the naming convention of stars and their exoplanets. All stars and exoplanets have alphanumeric designations. So these are alphanumeric designations, but very few have proper alphabetical names. Okay. In recent years, the International Astronomical Union has started the process of adopting proper names for exoplanets. The first giant exoplanet discovered in 1995 by Michael and his students were named this. I can't pronounce that, so that's it. Then, spoiler alert, this project is not about discovering new exoplanets. Sorry. It is not about discovering new exoplanets. Okay? So bear that in mind. However, it is very important. It is a follow-up study of already discovered planets by the TESS and Kepler missions and more. Okay? There has been these missions space missions that were sent about a decade ago to study to detect if these stars have exoplanets around them, and they did well in discovering about 5,000 exoplanets. For the first time, we got to understand that these stars that we are seeing in the night sky somehow have some planets around them. Then, so the purpose is correction for the exact mid-transit time of exoplanets. The mid-transit time, you want to correct them. The aim is to support the future missions of the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, which will study the atmospheres and habitability of this exoplanet. Let me explain this further. What are the reasons? Now, the James Webb Space Telescope was built at a cost of 10 billion US dollars. 10 billion US dollars. And it's expected to have a lifespan of 5 to 10 years. That is the lifespan. So if you do the math, you would get that the cost of operation is between $30 to $60 per second. So if you divide the money over the time, you would get $30 to $60 per second of telescope time. So imagine that you're a PhD student and you want to use it for research, and you have just wrote a proposal for grants. You have to be very careful so that you don't waste even a second. I hope you are seeing the picture. We want to correct the mid-transit time of this exoplanet so that we don't have to waste extra second in waiting for the exoplanet to come, because some of these exoplanets have long periods around their host stars. So it is extremely expensive and very, very competitive. So if you do not have enough data that will enable you to save time, you may not even win the observation time on the James Webb Space Telescope. So that is why we are contributing to this research, so that researchers can always use it to know when these exoplanets will be orbiting. So, but with our own telescope, you can always waste all the time you want. But for the James Webb Space Telescope, we don't have to waste a second. Therefore, the James Webb Space Telescope needs to know where and when to look, even in seconds. So imagine that you have a meeting by say 3 p.m. Okay, maybe Zoom meeting. You are expected to be in that meeting, let's say by 2:55 or even 2:50 p.m. So it makes you look like a very diligent person. But imagine that you come by 3:10 p.m. it's a whole mess up. Imagine it's a job interview and it's online. You already lost it. So that is why we are saving time, even in seconds. So it's exactly what we are doing. So imagine that we want to observe these exoplanets, and it is now coming. So we now focus the James Webb Space Telescope, and now it is taking the light curve. It's exactly what we want to do. We don't have to wait for it forever. Maybe waste 3 hours or 4 hours or even seconds. We just want to take the the data when the exoplanet is orbiting the host star. So there are several exoplanet research projects. We have the DIY Planet Search. So it's a group work, okay? Then we have the Exoplanet Watch. Then we have this one we use a Python program called Exotic to perform data reduction, okay? But this one you have to do it manually. Then we also have the ExoCloud project. We have the HOPS tool. It is also a tool for performing the data reduction. You can also do it alone. Then we have the Exoplanets Transit Database project. However, these two are, I think, from European Space Agency, and these are from NASA projects. So this is one of the most serious research, citizen science research areas in astronomy. Then data sources. Where do you get your data? All right. In the asteroid search, we get our data from ISAC, okay? From ISAC. But here you have to get your own data. And where do you get them? First of all, for beginners, you can get it from the NASA Exoplanet Observation Data Checkout. You will receive one set of data sets containing 20 to 200 images per 2 weeks. Every 2 weeks you get the data. I'm going to demonstrate to you how to do that, okay? Then we have the Micro Observatory, MOPS. Micro Observatory, you can also use a telescope network of the Micro Observatory to capture your own images and later download them, and I'm going to show you that. This is the Micro Observatory, okay? It is located at Harvard University. Then you can also use any Webb telescope, like the Loscombe Observatory. We have about 100 hours of telescope time with the Loscombe Observatory, and we are using it for this research. So if you're interested in using some part of the time, we can allocate that to you. And we're going to prepare a video on how to do that. And the Loscombe Observatory, or not just the Loscombe Observatory, but any Webb telescope that is above 15 centimeter in diameter, okay? You can use your own telescope, okay, whose diameter is between 15 centimeters, above 50 centimeters, okay? It must have a camera, okay? Then, to make things easy, okay, I'm going to start by, I have loaded some data sets in our bank, okay, Pascal data set bank, okay, so that you can start from there, okay. In order not to make you to go through the hurdles of these steps as a beginner, we have loaded some data sets into our bank. We call it the Pascal data set bank. So as a beginner, you're going to be working with those data sets, okay? It is not like the asteroid search where you have old data set and a new data set. There's nothing like old and new here, okay? All data sets are still valid. Then skills, requirements, and more. So first of all, we need to obtain an observation code, the AAVSO observation code. I'm going to walk you through that step in this video. You must have a Gmail account. You must have a Gmail account to be able to run the program. You do not need it to register. You can use any email of your choice to register, but you need a Gmail account to run the program. No software installation is required. All the tools are web-based. Consequently, you can use any device that can access the internet, example, smartphone, PC, any operating system is allowed, and tablet. but for the best experience, PC is advisable to be used. Okay, because there's no software installation, so it means that everything is well based, and it means you can actually use your smartphone. However, I've not used my smartphone, I've not used a tablet, but you can, find your way through that. Then you need a pattern recognition skills. Then you need a piece of paper and a pen to record your readings. You have to keep it by your side. Then you have to know that this is a little bit complicated than Isaac asteroid hunting. Okay, it's a little bit complicated. You have to bear that in mind. However, by the time we are done with the training, it becomes very easy. But it's not as simple as the asteroid search. Then the reward, no certificate is issued for now, but your works are published on the AFVSO website where the members of the public can see them, and NASA will use them for future missions. If you are a citizen scientist participating in the Exoplanet Watch, you will be listed as a co-author on scientific papers in the peer-reviewed journals if they use your light curves in their research or in their publication. You don't have to write your own scientific paper in order to contribute to the global body of scientific knowledge about transiting exoplanets. So oftentimes you will hear some members in the Slack, because we have a Slack community of those participating in this exoplanet research, and I'm going to show you how to get there. So this is a typical example. One member could just have interest in writing a paper with the data reduction of several other persons. So you could just make an announcement. For instance, here you say, "Hi, folks. Uh, Friendly reminder: if anyone has data on this exoplanet system and would like to be included on the publication, the criteria are as follows: data must be from this year, that is 2023, or to be included in the ephemeris update. The exotic must be used to be able to submit the data. The publication is based off of exotic data and to show off what exotic is capable of doing and what we are capable of doing as a group as well. We are doing this publication to show other groups that our group, that both amateur and professional astronomers working both side by side to provide better up-to-date follow-up on both already confirmed exoplanets and exoplanet candidates confirmation, as well as to show that anyone can also learn this and get involved with the scientific outreach in exoplanet research. So you typically hear this, and once you hear this announcement, what you have to do is to go there and schedule an observation, get the data, perform light curve, produce a light curve, and submit it, and you just become part of the co-authors. That is just what is required. So these are the typical example of the light curves you shall be producing. This is the light curve, okay? So this is on this Carter 1b, it's an exoplanet. So with the observation from the person that submitted this, he started to observe it earlier on. So then he got these light, this dip here, this dip. Then, and it came back to its normal baseline and started to go behind the whole star. Then here is this person that made this observation started quite late when the planet has started to orbit around its own star. And this is exactly what we want to avoid. We don't want to start observing this exoplanet with a James Webb Space Telescope when they have started to transit. Okay, and this person started quite on time, but could not wait long enough to take the whole data. And this one seems like either the planet is very small or maybe the person did not perform the light curve very well. So these are some of the different kinds of light curves you are likely going to encounter from the data. Then there are some common terminologies you shall be familiar with in this research. Number one is DOCS. A DOCS file is a type of calibration file that is used in astrophotography to reduce the noise and correct the defects in the images of the night sky. It is taken with the camera lens or telescope cover. This way, the DOCS 5. Captures only the noise and defects of the camera sensor, such as the hard pixels, cold pixels, and thermal noise. By subtracting the darks 5 from the light frames, the noise and defects can be removed, resulting in a cleaner and more accurate image. Then we also have target stars. Target stars are stars under investigation. Then we have comparison stars, also called COMSTARS, are stars that are used to measure the brightness of other stars or celestial objects. They are usually chosen to be nearby target stars. They are stable and well-studied stars with known magnitudes. AAVSO stands for the American Association of Variable Star Observers. It's an international nonprofit organization that focuses on coordinating, analyzing, publishing, and archiving variable star observation made largely by amateur astronomers. Variable stars are stars that change in brightness over time due to various physical processes such as pulsation, rotation, eclipses, flare, or explosions. I want to also let you know that this is not typical for Americans. Anybody can be part of this community. American Association of Variable Star Observers is not particular for Americans. So we shall go into the training.